Now, whenever I've used Google search in the past, I've often only entered keywords such as dressage goal. It turns out that Google search uses BERT. BERT, which stands for Bidirectional Encoder Representations from Transformers, is a large language model that was developed by Google. BERT is based on the transformer architecture and composed of transformer encoder layers, which we looked at in a previous video. Since Google uses BERT, we get better language understanding. This means I don't just have to use keywords, but I can enter a question like, what's the main objective of dressage? And the answer back from Google doesn't just give me the most relevant page, but the answer to my question is highlighted. So the main objective of dressage is improving and facilitating the horse's performance of normal tasks. Here's another example of BERT in production. In the past, if you did a Google search using the phrase, "Can you get medicine for someone pharmacy?" it wouldn't have picked up on the fact that for someone was a really important part of the query because you're looking for another person to pick up the medicine. Google search would have returned results about generally getting a prescription filled, which isn't relevant in this context. Now, with BERT, Google search captures the important nuance that another person needs to pick up the medicine, and it returns results about having a friend or a family member pick up a prescription. BERT is around 110 million parameters and was trained on the English Wikipedia and books corpus, which are 11,000 books written by yet unpublished authors. And unlike text generation models like ChatGPT and GPT-4, where they're trained to generate the next token, BERT is trained on two other tasks: masked language modeling, or MLM, and next sentence prediction, or NSP. The masked language modeling task requires BERT to predict a masked out word. Let's take a look at an example. The MLM task requires BERT to predict the masked out word. So the Tokyo Olympic Games were something from 2020 to 2021. The answer here is that the Tokyo Olympic Games were postponed from 2020 to 2021. If BERT doesn't guess postponed during training, the weights in the network get adjusted so that it's more likely to guess this word the next time round. The next sentence prediction task asks the question, does the second sentence follow immediately after the first? So, does the sentence, "This is the first instance," and so on, logically follow from "The Tokyo Olympic Games were postponed from 2020 to 2021"? Now, when would you ever need either of these tasks, and why are either of them useful? These tasks force BERT to get a really good understanding of language, and we've seen it so good that Google incorporated it as part of its search. All right, so we've seen that BERT doesn't generate text, but it's great at language understanding. Recall that transformer models have encoders and decoders. BERT is the only encoder model we look at. The rest of the models will be decoder only models. Right after BERT, research from OpenAI suggested that bigger models are better, and so the rest of the models we look at are truly large with billions of parameters. Imagine what things must have been like in the tech space in 2020. The transformer architecture in 2017 was proving to be better than anything before it. This is a time of significant experimentation. Some companies were focusing on the decoder portion, others on the encoder. Others were trying to figure out how they could make the models even better. And it was at this time that the research team at OpenAI suggested that the performance of large models was a function of the number of model parameters, the size of the dataset the models were trained on, and the total amount of compute available for training. They performed several experiments on language models to back up their claim. Let's take a look at some of the results. So, on the y axis is the test loss, and a lower test loss indicates that the model is performing better. Along the x-axis is the number of parameters in the model. So you can see that the x-axis isn't linear. We have markings for 100,000, 10 million, and 1 billion parameters. Now, because the graph is sloping down, there seems to be a trend where the bigger the model, so the more parameters it has, the lower the test loss. So how do you make models larger? One way you can do this is to have more layers. So that's more encoder or decoder layers from a transformer architecture. The graph in the middle plots the test loss versus the dataset size. The dataset size is referring to the number of training tokens. This is the data the model was trained on. From this graph, you can see that there's again this striking trend. The larger the dataset size, so the more data the model's trained on, the lower the test loss. And finally, let's look at compute. So over on the graph at the right, the x-axis shows the number of petaflop compute days, which is the amount of compute used for training models. Each of the blue lines correspond to the learning curves of different models of different sizes. The reason that this moves to the right is that bigger models require more compute capability to train on. But we can see that the test loss reduces. A lower test loss means that the bigger models perform better. The dotted orange line is the maximum amount of performance you can get for a given amount of compute. So, what this graph is saying is use a large language model based on the size of the compute budget. Now, if we take all three graphs together, they're telling us that language modeling performance improves as we increase the model size, the amount of data for training, and the amount of compute used for training. So, for best performance, all three factors must be scaled up together. The OpenAI team then went on to propose that as more compute becomes available, you can decide where you want to allocate it by training a larger model, using larger batches, or training for more steps. Now, training for more steps means training the model for a longer time. They concluded that most of the increase should go towards increasing the model size. Now, there is some benefit to using more data and using larger batch sizes, but minimal contribution if you train the language model for more steps. So, when the results from these scaling laws were published in 2020, it wasn't surprising that many big tech firms went down the route of increasing the model size and so creating larger language models. OpenAI released GPT-3, which was 175 billion parameters. This was significantly better than any other language model at the time, and we look at this model next. GPT-3 is probably one of the most well-known large language models. Let's take a look at what the letters GPT represent in turn. So G is for generative, as we are predicting a future token given past tokens. P is for pre-trained, as it's trained on a large corpus of data, including English Wikipedia, amongst several others. This involves significant compute time and costs. And finally, the T corresponds to a transformer, and we're using the decoder portion of the transformer architecture. GPT-3's objective was simple. Given the preceding tokens in the example, it needs to predict the next token. So this is like predictive text on your phone. So if I gave it the phrase once upon a, the most likely next token is time. Once upon a time. Remember that a token is a subword. So these are known as causal or autoregressive language models. For a couple of years, the focus of researchers was getting a large corpus of data and then training a language model. Now, if you wanted to use the language model for a specific task, say sentiment analysis, then you'd need to give it hundreds of examples of sentences that were labeled as either having a positive or negative sentiment and train the model on these sentences and labels. And the model would produce excellent results. Now, sentiment analysis is where you provide a text as input to the language model, and the language model needs to then predict if the text has a positive or negative sentiment. So here's an example from the movie reviews. Brilliant execution and acting, excellent work by the director, cast, and crew. And this is labeled with a positive review. So now let's take a look at a negative example. This piece ain't really worth a comment. It's simply the worst horror movie I've ever seen. The actors are bad as bad can be, and the whole plot is so silly, it nearly made me cry. Now, models like BERT are excellent at these types of tasks. And after being trained on a couple of hundreds of examples, if you give it a new movie review that it hasn't seen before, it would get it right more than 95% of the time. Now, let's say if you have a totally different task like question answering. Now, this is where you provide a text to the model and you ask a question and you want it to extract the answer from the text. So, let me give you an example. Now, let's say the text is the Summer 2020 Olympics included new disciplines such as baseball and softball, surfing, and skateboarding. It was hosted in Tokyo, Japan. And if the question was, where was the 2020 Olympics held? The answer would be Tokyo, Japan. Now, if you try to use the same language model that you used for sentiment analysis to perform this question answering task, it would fail miserably. You'd have to start again with your initial language model, make a few changes to the model architecture, give it a couple of hundred examples of sentences where for each text you have questions and the correct answers, and train the model, and it would eventually get good at this task. But the OpenAI researchers argued that what makes this different to how you and I operate is that if we have to learn a new task, we can do a reasonable job if we're given a clear set of instructions and a couple of examples. So, what the researchers found was if they created a really large language model, So the 175 billion parameters in the case of GPT-3. And if they gave it a new task and a couple of examples with the expected output, it was able to perform these tasks. So let me show you an example using sentiment analysis in the OpenAI playground. I'm now in the OpenAI playground, and I'm now going to ask the model to classify the following text. So this is my text, and I'm going to say classify the following text as being either positive or negative. And let's see what response we get back. So you can see that the language model generates a whole load of text. So probably one of his worst films and a disrespect to the original novel, but still very funny in certain places and so on. Right? So this is an example of zero shot learning where we haven't given the model any examples. So let's go ahead and try and give the model a couple of examples and see how it performs. So I'm just going to reformat the text. So I'm going to call the text review, and then I'm going to say that this has a positive sentiment. Now I'm going to give it another example, and this is what's known as few shot learning. So if I just give it a single example, that's known as one shot learning. If I give it a couple of examples, this is known as few shot learning. So let me go ahead and provide an example of a negative sentiment. So that's the review. And again, let me use the same format. So review, and I say that this has a negative sentiment. And finally, let's give the model a review that it hasn't seen before. And this time around, the model needs to figure out whether this is positive or negative. So this is known as few shot learning because we've given it two examples. And you can see that the model correctly classifies this as negative and then goes on to generate more text. So let's go ahead and just make a couple of changes to our settings. So because we only wanted to generate either positive or negative, I'm going to go ahead and specify that the maximum length needs to only be 1. So it's going to generate either negative or positive, that meaning a single token. And let's go ahead and remove all of the text that we had before. And now let's go ahead and submit this. Okay, I've got a warning that my text ends in a trailing space. So let me just go ahead and try and just delete that. And let's try again. So I'm going to go ahead and select submit. And you can see that the model correctly classifies this as a negative sentiment. So what's special about what we've just done is that we've now used a large language model that wasn't trained on sentiment analysis to do this task just by providing a couple of examples. Now, its accuracy isn't going to be as good as a BERT model that has been trained for this task. But what we could do is give it another task with a couple of examples. So given this text and these questions and answers, go ahead and answer this question, and the model will get reasonable results. Let's go ahead and take a look at the model sizes. You might still question why the OpenAI researchers went for such a large model, given that most models were a couple of billion parameters at most at this time. This graph summarizes their findings. GPT-3 is a family of models with sizes 1.3 billion parameters, 13 billion parameters, and 175 billion parameters. Across on the x-axis is the number of examples you're giving the model. On the y-axis is the accuracy of the model for a task. The higher it is, the better performing a model. Over on the top of the graph, you have labels 0 shot, 1 shot, and few shot, which is how many examples you're giving the model for the task you wanted to perform. Let's take a look at the smallest model, the 1.3 billion parameter model. Regardless of how many examples you give it, the accuracy of the model is pretty low. It's less than 10%. The 13 billion parameter model is slightly better. The more examples you give it, the better the accuracy, but it's still around 25% at most. With a 175 billion parameter model, giving it just one example boosts the accuracy up to almost 50%. So if you give it a couple of examples for a new task, the accuracy is more than 60%. Now, this is really impressive for a model that hasn't been trained on one specific task. This larger 175 billion parameter GPT-3 model is able to make use of the examples that you give it in a way that the smaller GPT-3 models were not able to. So let's summarize our understanding of GPT-3 in a table so that we can compare it to BERT. One of GPT-3's primary objective was few-shot learning. This performed best on the largest of the GPT-3 models, the 175 parameter model. Over the years, the trend has been to increase the model size. Although we won't look at any of these models in detail, I'll mention them briefly now because we'll be comparing them later. So, Megatron Turing was released by a collaboration between Microsoft and NVIDIA in Jan of 2022 that had 530 billion parameters. The Google DeepMind team released details about Gopher, which had 280 billion parameters, and it was one of the best models out there at the time. You can see that the model sizes were getting very large, and this was because of the scaling laws. But what if the scaling laws didn't capture the entire picture? The DeepMind team's hypothesis was that large language models were significantly undertrained. You could get much better performance with the same computational budget by training a smaller model for longer. Now, the way you would try and test out a hypothesis is to do a whole load of experiments, and that's exactly what the Google Mind team did. They trained several hundred language models. They varied the sizes of these models from 70 million to over 16 billion parameters. And then they trained them with different amounts of data from 5 to 500 billion tokens. Based on their hypothesis, they then created and trained Chinchilla, a 70 billion parameter model on 1.4 trillion training tokens. Now, one of the key benefits of Chinchilla was that it was a smaller model. This meant less compute was required for fine tuning and inference. Now, remarkably, the 70 billion parameter Chinchilla outperforms Gopher, which has 280 billion parameters, GPT-3 with its 175 billion parameters, and Megatron Turing with its 530 billion parameters on a large range of language tasks. Now, let's think back to what we learned about scaling laws. One of the key insights in this paper is that if you were training a large language model and you get a tenfold increase in the computational budget, the majority of that should go towards increasing the size of the model and a smaller proportion towards the number of training tokens and training the model for longer. The DeepMind team behind the Chinchilla paper confirmed that it was important to scale the model size and the training data as suggested by the scaling laws. But unlike the scaling laws, the size of the model did not need to grow faster than the amount of training data. So, for a tenfold increase in computational budget, the model size and the number of training tokens should be scaled in equal proportion. Let's take a look at how they demonstrated this. Firstly, you'll notice that both the x-axis and the y-axis are not linear. The x-axis goes up by hundreds and the y-axis goes up by tens. Now, the reason they've done this is because the quantities that are being measured increase by large amounts, and you'd not be able to show this relationship easily on a graph otherwise. Now, on the x-axis, we have flops or floating point operations, and these are a measure of computation. So the further you go across on the x-axis, the more expensive it is because you require more computational resources. On the y-axis, we have the number of parameters for the models, so that's the size of the model. And as we go up, the models are getting significantly larger. So on the graph, you can see that we have the GPT-3 model that's represented by the red star, the Gopher model that's represented by the yellow star, the Megatron Turing model given by the purple star, and finally the Chinchilla model represented by the green star. Chinchilla outperforms Gopher, GPT-3, and Megatron Turing. This means that it's better at a wide variety of tasks like reading comprehension and question answering, answering questions on a variety of different topics at high school level from history to chemistry to astronomy. Now, what's interesting is that it was trained on the same amount of compute as Gopher. Now, I can confirm that because if I draw a vertical line from the green chinchilla star down all the way down, Gopher would also be on this line. And this means they were trained having around the same amount of compute. So, the takeaway from this is that chinchilla is significantly smaller than the other models. And you can see this on the y axis, but it was trained having around the same compute, and yet it outperforms them all. Let's take a quick look at the data that the models were trained on. While most of the large language models have been trained on around 300 billion tokens, Chinchilla has been trained on 1.4 trillion tokens, which is almost 5 times as many tokens as the other large language models. This then begs the question, are the massive language models that are being trained oversized? So let's say we use the Gopher model as our baseline. Remember that the Google DeepMind team released Gopher, which had 280 billion parameters. For their compute budget, the optimal model parameter size should be 67 billion parameters, and the number of training tokens 1.5 trillion tokens. Now we know that the number of training tokens for Gopher was 280 billion parameters. This means that their training budget should have actually been 17.2 times more, and they would have required 5.9 trillion training tokens. It doesn't mean that you can't train these large models. It's just that these language models have not been trained with enough data. The DeepMind team designed an interesting experiment to compare their findings with the scaling laws. Given a compute budget of a certain number of flops, determine the number of parameters required and how much data is required to train it using the scaling laws prescribed by OpenAI and the ones determined by DeepMind. Whichever language model results in the most performant model is better. Now, the way you can compare and determine which model is better is if you give it a whole load of tests from generating text to question answering to high school questions on a variety of subjects, and you can see which one gets the most correct answers. With the scaling laws from the OpenAI team, the flops budget recommended a 4.68 billion parameter model. DeepMind's approach recommended a 2.8 billion parameter model. So the results from using the chinchilla paper are in blue, and the results from using the original scaling laws are in orange. The y-axis is the training loss, so the lower, the better. The x-axis represents the number of training tokens. You can see that if we stopped at the number of training tokens recommended by the scaling laws, the orange curve is lower than the blue one, and it would appear that it has a lower training loss, and so it's a better performing model. However, because the chinchilla paper recommends that the model needs to be trained on more data, we can see that the blue chinchilla curve ends up with an overall lower training loss compared to using the scaling laws given in orange. Similarly, if we were to just plot the training loss versus the number of training flops or floating point operations in the diagram on the right, you can see that we get a lower loss using the chinchilla method in blue versus the scaling laws in orange. So it turns out that you can end up with a more performant model using a smaller model with more training data. So let's wrap up this section by adding Chinchilla to our list of models. I'm also going to add Megatron Turing and Gopher, even though we've looked at them briefly. Our biggest takeaway is that up to this point, large language models are significantly undertrained. And from the table, Chinchilla is trained on more than 4 times as much data as any other large language model. It's the smallest, but also has the best performing results. Lessons from Chinchilla have helped me at work. At a project for a customer, we were looking to train a model from scratch on a European language. We looked at the size of the model and the size of the training dataset we had and quickly realized that we would not get a performant model because we didn't have enough training data. So instead of kicking off a training run, we focused our efforts on getting more training data. We're finally at one of the largest language models to date. Google released PaLM, or to give it its full name, the Pathways Language Model, in April 2022. There are a couple of key takeaways from the PaLM model. PaLM is the largest model with 540 billion parameters. Google uses the pathway systems, which meant more hardware accelerators could be used for model training, and they could be trained more efficiently. PaLM was trained on an enormous 780 billion tokens multilingual corpus with text from over 100 languages. Now, just over 3/4 of this training data was in English. Another really interesting phenomena that the Google team picked up on was on scaling. It looked like the models could only perform certain tasks once a certain scale was reached. Here, 8 billion parameter models could perform certain tasks such as question answering, language understanding, and arithmetic. It was only when the model was scaled up to 62 billion parameters that more tasks such as translation, summarization, and common sense reasoning were possible. But it then required a much bigger jump to 540 billion parameters for the model to be able to perform tasks such as general knowledge, reading comprehension, and joke explanation, amongst others. PaLM is the best performing model of the lot, outdoing Gopher and Chinchilla on the standard benchmarks that measure natural language understanding and natural language generation tasks. Let's add PaLM to our list of models. You can see that it's the largest model to date, and although it wasn't trained on as many training tokens as Chinchilla, it performs the best. If we take the lessons from the Chinchilla paper, it means that although the PaLM model was trained on 780 billion training tokens, which is more data than the 380 billion that was used for other models, it's likely that it has still been undertrained and could perform better if trained on more data. In May of 2023, Google released PaLM 2, which surpassed the capabilities of PaLM. Now, because of the increasing competitive nature of the large language model space, Google has not released information on the size of the model nor the amount of data it was trained on. PaLM 2 was trained on more than 100 languages, meaning it's able to understand and generate text that is more nuanced. It has also passed advanced language proficiency exams at the mastery level. Scientific papers and pages with mathematical expressions were part of the vast training dataset that was used to train Palm 2. And as a result, it's even better at logic and common sense reasoning and mathematical tasks compared to the original Palm model. Palm 2 is also trained on a large quantity of publicly available programming code. This means it's not only excellent at generating code or correcting code in popular modern languages like Python and JavaScript, but it can also generate code in languages like Prolog and Fortran and Verilog. And what's remarkable is that Palm 2's smallest model will be able to run on mobile devices. Palm 2 will be used to power features in the other Google products like Gmail and Google Docs, and also expand BARD, which is another large language model released by Google. One of the other benefits of Palm 2 is that it's been used to train MedPalm 2 that has been trained by Google's health research teams. This is the first large language model to perform at expert level on US medical licensing exam style questions. The Google team are adding multimodal capabilities. This means you could feed it an X ray image and then ask the model to analyze the X ray image and report on its findings, and then potentially query the model further on the image. Let's add Palm 2 to our list of models. It looks like Palm 2 is Google's best performing model and it'll be powering many of its products. ChatGPT launched on the 30th of November 2022 and had 100 million monthly active users 2 months later. But what's the difference between GPT-3, ChatGPT, and GPT-4? GPT-3 could generate text, and we saw earlier that it does a great job of it. The only problem is it doesn't follow instructions. GPT 3.5 was an upgrade on GPT 3 by allowing language models to better follow instructions using supervised fine tuning and RLHF, or reinforcement learning with human feedback. You might remember these terms from the first couple of videos of this course. This is when language models try to respond to prompts like human labelers. ChatGPT is fine tuned from GPT 3.5 and was further optimized for dialogue, so you could use it like a chatbot. ChatGPT can also do other things like helping programmers write programming code. GPT-4 was released in March of 2023 and takes things further. It's a bigger model than ChatGPT and can do more complex reasoning, and is the best model for complex tasks like cause and effect or logical reasoning at the time of this recording. It also achieved human level performance on many high school advanced placement exams, ranging from statistics and biology to art history and psychology. Earlier, we said a language model is something that takes in text input or a prompt and outputs text data. Now, it turns out that GPT-4 is multimodal. This means it can take in either text or a combination of text and image data and will output text. And at the time of this recording, you can only submit text data as input to GPT-4. Those of us who use large language models are always curious about the data and the model architecture used to train the model. But this time round, OpenAI has decided that they won't share the results. In their GPT-4 paper, they say, given both the competitive landscape and the safety implications of large-scale models like GPT-4, this report contains no further details about the architecture, including model size, hardware, training compute, dataset construction, training method, or similar. Now, although GPT-4 performs very well, it has some limitations. There are at least three areas that need some work. Firstly, you can't fine tune the GPT-4 models, and GPT-4 doesn't update its knowledge in real time. It was trained with data up to September of 2021, so it has no knowledge of anything that has happened since. And finally, sometimes it makes up facts. Now, if a model like GPT-4 performs so well, why would you want to fine tune these models? Well, let's say you were working in a very niche area like the latest research on seaweed biology and writing academic papers. It's likely that the GPT-4 model hasn't been trained on academic papers in this space as it's so unique. So there'll be terms that are unique to these academic papers that the GPT-4 model will have no context for. Fine-tuning a model with these kind of academic papers is likely to lead to a better performing model if you have some other NLP tasks like text classification. The only problem is that although the GPT-4 models are very capable, they can't be fine tuned as of the time of this recording. So if you want to fine tune a model on this specific data set, then you'll need to use the original GPT-3 model. Let me show you two other limitations while I still have the OpenAI playground open. Now, I don't know what output this GPT-4 model is going to generate, but I'd like it to write a catchy introduction to the topics I'm covering in this course. So let me go ahead and just use some of the topics I'll be covering as input. So this is my prompt. These are the topics I'm covering in an introduction to the large language models course. Write a catchy introduction. So what are large language models? GPT-4, limitations of GPT-4, and Helm. Now, although the output that's been generated is very impressive, there are a couple of problems here. If I scroll down to the bottom, and let's look at this section here. So GPT-4 generates, besides GPT-4, we'll also delve into some exciting new entrants in the field like Helm. This makes it sound like Helm is another large language model. In fact, Helm stands for the Holistic Evaluation of Language Models, and it's a benchmark to allow you to compare language models. Now, since the Helm benchmark was released at the end of 2022, this means that GPT-4 doesn't have any knowledge of it. There is a workaround where OpenAI have released plugins which allow you to reach third party information sources, including the internet. All right, so we've seen that we cannot fine tune the GPT-4 models. It doesn't update its knowledge in real time, so it was trained on data up till September 2021, and it has no knowledge of anything that has happened since, and it sometimes makes up facts. Go ahead to the OpenAI playground and try out GPT-4 and ask questions about a topic that you're reasonably skilled in, and then have a dialogue and see how good the GPT-4 model is. I think you'll find the results are very impressive. Now let's go ahead and add ChatGPT and GPT-4 to our table comparing the large language models. ChatGPT was incredibly popular as soon as it was released. GPT-4 has human level performance on various exams and is the best performing model at the time of this recording. We've looked at models that have all come from big tech firms like Google and OpenAI, but what about open community models? Now, although OpenAI made GPT-3 available via an API or the playground, which is what we've seen so far, no access was given to the actual weights of the model. So, if you had access to the weights of the model, you can tweak and experiment with the model to create new variations that might be better suited for specific tasks. For example, you can try and create smaller versions of the model. Meta released OPT or Open Pre-trained Transformers. This is a couple of decoder only pre trained transformers ranging from 125 million to 66 billion parameters, which they shared with anyone. And interested researchers could also apply for access to the 175 billion parameter models. This effectively gave researchers access to a large language model that was very similar to GPT-3. The Meta team also detailed the infrastructure challenges they faced, along with providing code for experimenting with the models. This model was primarily trained on English text. A couple of months later, Hugging Face, which is a company that provides a machine learning platform to store models, think of it like GitHub for models. Well, their research team received a grant for computing resources from the French government, allowing them to train the Bloom model. Working together with a volunteer team of over 1,000 researchers from different countries and institutions, they created a 176 billion parameter model called Bloom. This team has made everything openly available from the dataset used for training to anyone being able to download and run this model. This allows other organizations outside of big tech to experiment with these models. Now, even if you want to run these models, you still need access to expensive hardware accelerators. Now, despite all this collaboration, the performance of these models was still lagging behind the likes of the OpenAI models. This is probably because, given this is a new field, not many engineers have the skills and experience working with hundreds of hardware accelerators in parallel and the associated problems. The majority of the engineers working for big tech companies like Google and OpenAI and Meta have had a couple of years head start on others. In February of 2023, Meta released the Llama models, which are 7, 13, 30, and 65 billion. with a license only allowing them to be used for research and non commercial purposes. Given the excellent performance of these models on various open benchmarks, they quickly became the most popular open language models thus far. The weights for these models were available to the research community, but they were quickly leaked. Some researchers extended the Llama model capability by instruction tuning, others tried training it on non English data. This visual gives you an idea of how impactful Llama has been to the open community. Up to this point, we knew from the OpenAI research that training models with instructions significantly improves their performance. But OpenAI didn't release the dataset allowing others to try this out. Because of the excellent model performance of Llama, it's been used to provide the language component for many multimodal models. These are models that can take in different inputs, for example, text or images, and output either text or images. Over on the left, the Llama models were trained with Chinese data, providing a variety of different Chinese models trained on data for different industries like finance and law and education and medicine. I think one of the reasons that Llama was more widely adopted than, say, Meta's open pre trained model is because it's much smaller and so more readily accessible to anyone because you can easily run the smaller models on a single hardware accelerator like a GPU. This is the open large language model leaderboard available from the Hugging Face website. Let me just scroll down so that you can get a better look at some of the models. So this compares open large language models. In July of 2023, Meta released Llama 2. So this had a context length of 4,000 tokens and was trained on a whopping 2 trillion tokens. Now, what was remarkable was that less than a week after Meta released this model, teams in the open community produced better performing models. So, for example, you can see at the top of the leaderboard the stable Beluga 2, which is a model from Stability AI. At the time of this recording, derivatives of Llama 2 are the best open models out there. It's also worth noting that Llama 2 isn't fully open. Meta didn't release the training data. Meta also requires companies with over 700 million monthly users to ask Meta's permission before using this model. This affects a handful of fellow tech giants like Google. Now, why would Meta be willing to make all their models openly available? It would cost millions of US dollars in compute and data requirements to train such models. And one of the challenges with AI models is safety and how they're used. By making the models openly available, Meta can learn how the models are being used, and this allows them to make their own products, which would use some of these models more safe. Open models have got smaller and better over the years, closing the gap with closed models such as ChatGPT. So let's go ahead and add Llama 2 to our table comparing large language models. What's unique is that all of the Llama 2 models were trained on 2 trillion tokens, and it's the first set of open models that is comparable in performance to ChatGPT. How do we even compare large language models? That's a great question. I don't think we have a perfect answer yet, but we have made great progress over the last few months. Usually, we only focus on how good a model is at a task, but we don't know if that same model generates false information. So instead of just looking at one metric, a Stanford University research team proposed HELM, or the Holistic Evaluation of Language Models. With HELM, the Stanford research team worked together with the main large language model providers, and they were able to benchmark the models across a variety of data sets and get a more holistic view of model performance. The Helm benchmark is a living benchmark and should change as new models are released. I'll just cover the first couple of benchmarks and you can explore the rest further if you're interested. So let me just go ahead and scroll down a little bit. So here, each row corresponds to a different language model that has been tested, and each of the columns correspond to different benchmarks for different tasks. You can hover over each of the benchmarks. So, for example, you can see that this is MMLU, or the Massive Multitask Language Understanding Benchmark. And over at the right, you've got the CNN and Daily Benchmark, which is used for text summarization. Now, if you look at accuracy, the Text DaVinci 2 and 3 models, which are OpenAI GPT 3.5 models, have some of the best overall results across all of the datasets. GPT-4, which was released in March of 2023, doesn't feature in the Helm dataset yet. The robustness of models here is the worst case performance of the model. So, how does it perform when you send a text with typos or misspellings? And you can see there's some correlation here. Typically, models that have a high accuracy will be more robust. And again, we can see that the open AI models have high scores for this. Head over to the Helm website and dig into some of the other benchmarks like fairness and efficiency, bias, and so on. Because this benchmark is updated periodically, there might be some changes to what I've shown you here. It's important to note that Helm does have some limitations. For example, users don't know if they can easily fine tune a model for their use case. Other important considerations like the price of models and the latency when using these models is not measured. And also the availability of the model to users, meaning is the platform available most of the time? Let's now compare open language models. Hugging Face offers an open large language model leaderboard that we've seen earlier that allows you to compare open source large language models. Like Helm, the models are evaluated on a couple of different benchmarks. ARC are reasoning challenges for a set of grade school science questions. HelloSwag, which is a test of common sense inference, which is easy for humans but challenging for state of the art models. MMLU, which measures a text model's multitask accuracy. So this covers 57 tasks across elementary mathematics, US history, computer science, law, and loads more. And finally, Truthful QA, which is a test to measure how likely a model is to reproduce falsehoods commonly found online. And as you can see, Llama 2 and its derivatives are currently at the top of the leaderboard. Now you can also compare the response of a couple of models to a single prompt using something like nat.dev. So this is the nat.dev playground. And let's wrap things up with a less serious example. So I want to get the models to explain a joke. So I'm going to select two closed models and two open models. So here's the joke that I want the models to explain. So explain this joke. I was going to fly to visit my family on May 3rd. My mom said, "Oh, great, your dad's poetry reading is that tonight. So now I'm flying in on May 4th." Now I've intentionally included the reference to May the 4th to see if I can trick some of the language models to see if there's a Star Wars reference. The explanation of this joke is that this person doesn't want to attend their dad's poetry reading. So let's go ahead and see how the different models perform. Go ahead and pause the video here and compare the different outputs from the four models. After reading them, I think you'll agree with me that the GPT-4 model produces the best results. Now remember that this illustration is only comparing the models for a single task. You'll want to be comparing models on hundreds and thousands of tasks to see which one performs best for your business needs. Ultimately, you are the best judge for which model works best for your business domain.